I'm Chris Williams from the University of Edinburgh, and I'm going to tell you more about sort of latent variable models for time series. So we'll talk about hidden Markov models, also about Kalman filters, and also some sort of fancier things, including some stuff about recurrent neural nets at the end. Okay, so first of all, I mean, as we've just seen from Yanis, there are a lot of examples of time series in all sorts of places. We can predict the future values of the series, and that's what Yanis was just talking about forecasting. But we might also do other things, like we might, for example, have an input of a speech waveform, and we actually want to output maybe some textual representation of what the speaker is saying. Okay, so that's a sort of input-output mapping rather than just kind of trying to predict say the waveform I'm going to make in 2 seconds' time. So that's one example of these kind of things, and we can have this in all sorts of places. We might try to pick up objects in video. We might have genes in DNA and all sorts of things like this. So, as I said, there's really two latent variable models we're going to talk about. One is the discrete state, the hidden Markov model, and one is for continuous space of latent variables. And we'll talk about the Linear-Gaussian HMM or the Kalman filter. So, as we've just been saying, we can see these dynamical systems models in all sorts of places, speech recognition, molecular biology, when, interestingly, the sequence isn't a temporal sequence, it's actually a physical sequence. We can have linguistic sequences and things like that. We can have spike trains in neural data analysis, all sorts of time series. So what I'm going to talk about in this part is about, first of all, what is a hidden Markov model, what's its structure, what are the inference problems that we have. It's a probabilistic model. We need to do inference in it. How do we do that? Then the question of, once we've actually learned that model, once we can do inference in it, we have to learn that model. So similarly to Yanis talked to you about the ARMA model, that he told you how to estimate the parameters of the ARMA model from data. Then we need to do the same thing with the hidden Markov model. If you want to read about these things, I'm pointing to 3 different books. Chris Bishop's book from 2006, David Barber's book from, I think, 2012, and also Kevin Murphy's book, also from 2012. There's also a great tutorial paper by Rabiner from, way back in 1989. So that's sort of what we're going to do on hidden Markov models. And yes, great. Okay, so really simply, where do we start? We start with a Markov chain. So we might have, say, some random variables, A, B, C, and D. And we have the joint probability of those factors as P of A, P of B given A, P of C given B, and P of D given C. So that's, and this structure here is the so-called Markov chain. It's a first-order Markov chain. So in a hidden Markov model, well, we're going to basically take that Markov chain, and so we'll call these latent variables Zs, Z1, Z2, Z3, Z up to Zn. And we'll hang off those things for some observations, and these are the x's. So obviously it's fairly obvious why it's called a hidden Markov model, because this bit here is the Markov model, but we don't actually observe the Markov model. We only observe some x's that are probabilistically related to the underlying z. Okay, so that's the intuition. So we said that in the HMM, the latent variable is discrete. It will have k states, and so then if we have when we have this transition here from, say, time 1 to time 2, there's a probability matrix of going, say, we're in state J here, we'll go to state K at the next time. So there needs to be a probability of that. So that's represented by the state transition matrix A. We will need these output probabilities as well. Here, the xn's could be, say, discrete, or they could be continuous. There's various choices. We also need to say what our initial probabilities of being in Z1 are. That's denoted by pi. And we'll say that at each n, basically, we'll have an indicator variable. So there'll be, this will be a k-dimensional vector. And the state that we're in, say I, z in I is equal to 1. And all the other components of z at that time will be 0. So it's just an indicator variable for z. This perhaps look rather complicated notation, but don't panic. Pi of z1 says basically just pick out the component that we're in. So if we're in state, I don't know, j, then we'll have pi j here, and all these other terms will go away. Right? Similarly, for these transitions, we're just picking out the element of the transition matrix that applies based on what state we're in at time n and time n plus 1. So then the good thing is that this is a nice probability model. Here we have it. We can just write down the joint probability. We can write down this Markov chain for the z's, and for each z there's an x hanging off it. So it will look like this. The joint over all the x's and all the z's, the probability of being in z1, emitting x1 when we're in z1, transitioning from z1 to z2, and so on. Okay, so that's all very easy. So that's the probability model defined by the hidden Markov model. What we can see, and similar to what Yanis was talking about before, basically by conditioning on a Zn, say Z2 here, we'll separate off the past and the future. So very precisely in directed graphical models, we can actually talk about conditional independence relationships between different variables. And because everything is mediated through this hidden Markov chain, basically if we condition on the z's, we can separate the past and the future. And similarly, so also the x's that are hanging off the z's. But one thing we can't do is actually we just condition on the n, so xn, because this is just hanging off the z, that doesn't block the past and the future. So that's the difference why if we have this hidden structure, then we actually have to condition on the latent variable z to give us this independence. Sorry. Okay, the other thing to see is that if you're used to mixture models, and you'll be used to then that there'll be some discrete latent variable, then really what's happening here is a hidden Markov model is like a sort of dynamical mixture model. Because in a mixture model, what you do is that for every data point, you draw the indicator for which component you're in independently, okay? But in the dynamical model in the HMM, we use this Markov chain, so we generate this Z depending on what the previous Z was here. So that's the kind of another way to think about an HMM. Okay. If you perhaps, certainly if you have a computer science background, you might like to think about finite state automata. So the representations I've been showing you up to now with the circles and arrows are probabilistic graphical models. But now if we think about this and we say basically there are a number of different states, so we said there are k states in the hidden Markov model. If we think about, say, this one having 3 states in this example, then we can have these transition probabilities. Let me see. Just trying to check how doesn't matter. If we're in, say, state 3 and we transition to state 2, then we have this A32, okay? So these are the way we can think about this as a finite state automaton. And we also have to think that we emit a symbol when we enter these states. So we have this conditional distribution of, say, x given S2. And this is, again, relating back to our mixture model idea. Okay? So that's just, if you're used to thinking about finite state automata, that's how to translate these things. Okay. So once we've got that, there are various inference problems we might want to attack. We might be interested in saying, so remember x here is the sequence x1 up to x big N. It's the whole sequence of observations. We might be interested in this joint distribution of all the z's given the x's. We might be interested in a marginal of that. We might want to do something else where we just take x1 up to x little n, and we're just interested in the z in at that time. So that's called filtering. We can also look further ahead. So if, say here, n is greater than s, we've got some history, x1 to xs, we predict. We can also do something called smoothing, where we have observations here, u, going beyond n, and we want to kind of pass information back from the future as well as from the past to predict n here, so that's smoothing. And we can want to calculate the likelihood, and we might also want to come up with the most probable sequence of z's that explains an x. That's called Viterbl alignment. So these are all sorts of inference problems that we might want to do in a hidden Markov model. And certainly one reason we want to do these is actually they'll be very important when we come to learn the model as well. So that's just a graphical representation of filtering, smoothing, and prediction. one thing to say is that we might think, okay, so if we took, say we had 3 states at each time, we might think that there are an exponential number of paths, exponential in n, the length of the sequence, but the key thing about hidden Markov models is basically through dynamic programming, or essentially through pushing sums through products, we can actually calculate, say for example, the likelihood of the sequence of observations in linear time, the length of the sequence, and k squared in the k states, because basically we have to consider every transition to every other transition at neighboring times. Okay, so one thing we talked about, we wanted to compute this posterior marginal. So just using Bayes' theorem, we can re-express things like this. We can then break up this guy here, P of x given Zn, into the sort of part of the x's that are coming from the past and up to the present, and then those ones that in the present, sorry, the future given the present, that's the xn plus 1 up to x big N given Zn, and we can do that because of the conditional independences that we just talked about a few minutes ago, and then we can pull this Zn into this term here, and then basically the reason for giving you this maths here is to talk about these notations alpha and beta, and these are standard notations in hidden Markov models. This is the so-called forward recursion, the alpha. This is getting up to observing x1 up to xn and being in state Zn, okay? And then the betas are the p of xn plus 1 up to x big N, given that we're in z little n. So that's the sort of future. So this is the past and the present, and that's the future. And so, yeah, the key thing is that these have a recursive prediction. Also, we can bear in mind that at any time, say n, then if we sum out over the possible states we can be in, so discrete probability, we just sum that out, that must sum to 1. There must be valid probabilities that sum to 1. And that tells us that we can calculate this P of x, which is the likelihood of the observed sequence, marginalizing out all the possible z's. We can obtain that at any time, actually, if we have the alphas and betas, like this. Okay. We also might want to call this P of Zn given x. We might call it another standard notation is gamma. That's the marginal at time n. Okay, so there is a recursive formulation of the alphas and betas. This is a nice exercise. If I had a bit more time, I'd work it on the board, but basically there's a nice forward initialization. So if you take the definitions of the alphas and betas, and say you write, so this is, say, alpha of Zn is this P of x 1 up to xn and Zn. If you then replace that by, say, alpha of n plus 1, and then you pull apart that thing, depending on the Zn's, introducing Zn and marginalizing it out, you can obtain these recursions. So that's nice. So the thing is we can recurse the alphas forward from initialization here. We know what alpha of Z1, this thing is nice and easy to calculate. Also, we can calculate the betas running backwards from the end. Actually, it turns out that the betas should be initialized as a vector of 1s. And if you do that, you can basically run these forward and backward recursions. And then, as we saw, you can calculate the probability, the P of capital X at any time. But a nice place, a kind of convenient place to calculate it is, say, for example, at time n, when you just run the alpha recursions forward and then just sum things up. So yeah, each step is order k squared because we're looking at all possible transitions from time n to time n plus 1. So that's the recursion formulae for the alphas and betas. We can do a similar thing, but I'm not going to go into the details. Calculating the Viterbl alignment, basically we calculate a whole bunch of things running forward. We get to the end, we choose the maximum, and then we follow the pointers back that we've created, follow the breadcrumbs back in order to actually find the optimal alignment, so the Viterbl alignment. One other thing that we might want to do is to calculate this joint probability of being in state Zn at time, being in Zn at time n and Zn plus 1 at time n plus 1. And again, we can relate this to the alphas and the betas, and also this emission probability and this transition probability. So all these things work out very nicely. The reason we really want these is when we want to do actually parameter estimation. So what we want to do, okay, so let's just try something. Who has heard, please put your hand up if you've heard of the EM or expectation maximization algorithm. Okay, certainly some of you. Okay, great. So the point is that the EM algorithm is used for when we've got hidden variables or latent variables. So of course, in the hidden Markov model, we've got these latent Zs, these latent variables. So a natural way for us to want to try and learn such a model or estimate the parameters of a model is to run something like EM. So we have these parameters. The trick is basically if we knew the true underlying Z sequence, then it would be very easy to estimate the parameters. In fact, it then wouldn't be hidden. And then we can just, certainly for the Markov chain, we can just estimate that by counting. I'll show you that on the next slide. But then the trick is that as we don't have the underlying Z sequence, what we do is that we use our current estimates of the parameters, infer those Zs, then update the parameters on the basis of those Zs, and then iterate that round. Okay, so that's, and under general conditions, this will converge to at least an optimum of the likelihood. Maybe not the global optimum, maybe not the one we want, but certainly an optimum. So yeah, just first of all, if we learn the Markov model, then it's sort of fairly intuitively obvious, I think, that if we're interested in going, say, from state I at time n to state j at time n plus 1, a natural estimator of that probability is to count the number of times we go from I to j and divide by the number of times we're in I and we go anywhere. Okay, and that's what this notation says. Okay, and then, and I'm just pointing out there's a nice paper that makes use of mixtures of Markov models. So that's the estimator if we knew the Zs. If we don't know the Zs, all we do is replace these indicator functions by the psi's, these probabilities that we estimated this joint probability of being in state I at time n and state j at time n plus 1. So basically, without worrying too much about the details of this, we can see that we get sensible parameter estimates like this, and as I say, there's a lot of statistical theory around the EM algorithm that shows us that this is a good thing to do. So for example, here I'm saying that if the output distribution is actually a discrete distribution, so the x's are discrete, then basically we just here we count the number of times that we output, we're in state j at time n, given that we're in state I in the latent space, and then we just normalize that out. So these equations, so EM when applied to the hidden Markov model is actually known as the Baum-Welsh equations. Okay, so the problem we're solving here is the parameter estimation problem. Okay, we've got this structure, we know how to do inference in it, and making use of those inferences, we can do learning in this model. Now, as Yanis was talking about, certainly we have, as usual in statistical models, we'll have questions of model uncertainty. You know, there are all sorts of models that we could fit, or certainly in hidden Markov models we could have different k, we can have different number of hidden states. So certainly we might have to address that. But these are in fact the sort of usual problems we face with model order estimation in statistical models. One slightly unusual example of this is actually work I did with my student Murray Allen quite a long time ago. One thing we might want to do is that if we're given the melody of a tune, we might want to actually think about inferring the harmony. Okay, now there's a lot of harmonic rules, certainly in classical music, about how we should do this, but one thing we could do actually is that we could think of the visible states as being the melody, and maybe we're going to represent those at the level of, quarter notes if you speak American, or crotchets if you speak British English. And the hidden states here are the harmony, so which chord, and potentially actually it's a little bit more complex than that, it might be which inversion of the chord it also is. So basically, in this case, actually, if we have, say, I think we did this on, chorales and this from J.S. Bach, then in that case, we actually have the harmony and the melody simultaneously, so we can train the hidden states, the hidden transitions, and also the hidden to output transitions without actually having to do EM. And then when you give me a new melody, which actually might not be by J.S. Bach at all, it might be your favorite pop song or something else, then you can actually harmonize it in the style of J.S. Bach. Okay, so this is a kind of fun example of hidden Markov models, but they're real workhorses for sequential data analysis. And if I'd been talking like 5 years ago, I'd have told you they're the things that drive automatic speech recognition and also, say, identification of genes in sequences. Probably now, certainly for speech recognition, I'm pretty confident that actually recurrent neural networks are the things that people are using. But certainly these are lovely models, and they're fun to play with. Okay, I think that's, yep. Let me see. Yeah, so just summarize. We thought of HMMs as models for a discrete latent state, and we've talked about these problems such as filtering and smoothing, and the other models. I mean, also if we want to fit them to data, we need to do EM. Well, that's the standard way to do it. There are other ways. And then, as I've tried to convey, there are many applications of HMMs. Okay, so let me pause here and just ask if there are any questions about HMMs. No? It's either all very clear or you're all asleep. Well, perhaps some of both. Okay, let me just find the second set of slides. So I want to move on from discrete state hidden Markov models to continuous states. Okay. So if you can read very quickly, you've just observed the rest of the talk, but we'll go through a little slower. Okay. So the second piece of this is about how if we have continuous state. So one very classical application of this might be in, say, in engineering, or if we want to track a plane over time, we observe sequentially maybe radar returns about where it is. We want to do inference on where a plane is. That's pretty important if you want to fly around the world, which many of us probably do. So we'll talk about Linear-Gaussian hidden Markov models. Then we can talk about some graphical models that go beyond that. So there's some nice variations or extensions of those two sets of models. I'll also talk about recurrent neural networks, which have become very fashionable over the last few years, and say a few things about this. So again, there are sections in the book by Bishop, the book by Barber, and the book by Murphy which relate to particularly to Kalman filters or Linear-Gaussian HMMs. So, we have a continuous state space, and in that situation, the filtering problem is known as Kalman filtering, due to Rudolf Kalman, who invented this in 1960. So, we have the same graphical model that we had before with the z's and x's, but now there's something different. The z's are continuous valued, and we're going to assume there's a dynamical model for the z's, and let me see. Okay, test time. Yanis talked about this model in part one of the lectures. So what is this model? It's a, AR1, it's a vector AR1, but good, well done, thank you. So so Zn plus 1 is, depends on some matrix A times Zn plus noise, so this is a vector AR1 model. And so these W's are assumed to be Gaussian with some zero mean and covariance gamma. And that's the model, and we've also got an output model, and in this case we assume that there's a linear relationship between the z's and the x's plus noise. So xn is c zn plus vn, and again, vn is Gaussian noise. And everything will be Gaussian. We'll initialize this in as Gaussian at time 1, and then we'll run inference. The great news about Gaussians is that because these predictive distributions are all Gaussian, like the forward dynamics and also the observations, the whole model is jointly Gaussian. That will tell us that we can do inference by working out the covariance structure of that Gaussian, but it also, because actually we have this Markovian structure here, we can also exploit that in terms of the inferences, and certainly we'll see that for the filtering equations. So let's see a bit more detail. We might be interested in defining at time n. We've observed the sequence x1 up to xn, and we have this latent zn, and that will be Gaussian with some mean mu n and some covariance vn. And that's just the definitions of those means and covariances. And then there's a recursive update for these things. So there's a time update. We can take Zn, we can push it forward through the dynamics to time n plus 1. That's kind of straightforward, because actually we saw the AR1 model that we were told about here. And so we can just push things through forward on the AR1 model. And then what we also have to do is bear in mind that we now condition on an additional x. We bring in xn plus 1, and that actually gives us some information about Zn. So yeah, the time update is quite easy. So we can sort of break this up. Yeah, the expectation there, and the covariance is like this. And then what happens is a measurement update. And so what you can work through all the maths to do this is, if we're doing a whole lecture course, we'd definitely do that. But in the interest of time, what we can see here is that, say, from the mu's, the mu got updated by taking the previous mu through the dynamics. That's the time update. And then we've got the measurement update, and we've got this matrix K here. And this is called the Kalman gain matrix. It depends on this covariance matrix Pn and the C's and also the noise matrices. So the key thing is there's a nice recursive formulation for the mu's and the v's, depending on the previous one, which is sort of what we'd expect from the autoregressive structure of the model, but we still actually have to work all that out. Okay, so that's the Kalman updates. Basically, how do we do learning in such a model? Well, we just covered that for the hidden Markov model. It's a model with missing data or latent variables. The obvious thing to do if you've seen enough statistical modeling is to use EM, and to do that we can do these inferences. We'll need to do inferences, say at time t and time t plus 1, and we can run in the same way that we calculated the alphas and betas in the hidden Markov model. We can calculate analogous quantities that we're going to need here. There's also some nice work going back quite a long time called on subspace models. So basically, you can also try to do decompositions of the data matrix and various lagged versions of it, and that can certainly help you to get an initialization of the parameters. So we can do the same kinds of things in that case. So let's take a very simple example. The dynamics are actually a random walk that Yanis was telling us about. Zn plus 1 is Zn plus Wn plus 1. And the observation model is that the x's are the z's plus some noise. Okay, so that's all very simple. If we let sigma squared, this noise here on the initial condition, go to infinity, then basically what we'll see is that, say, mu3, our estimate at time of z at time 3, is a weighted sum of the x's, which sort of seems reasonable. But what's kind of interesting is that the most recent x's are actually more heavily weighted. So 5/8 of x3, 2/8 of x2, and 1/8 of x1. And if we didn't have any latent dynamics, then, so Zn plus 1 was just Zn, then we get what we'd expect here. They're just averaging them. Because what this is telling us is that Well, if we want to know where we are now, we should pay more attention to the most recent observations because things could have changed. You know, the Z could have had evolved and had dynamics over time, whereas in this case it wouldn't have done. Okay, so that, you know, you can work through the maths, but it also tells you things that you'd expect to work out nicely. Okay, so yeah, it's just a nice quote that the Kalman filter is a great way to kind of strip out noise out of a stream of data, and it's, you know, it's used in a lot of places, in GPS, you know, in radar, sonar, satellite, and so on. So, you know, these are important tools in, you know, in real-world applications. One thing we can do is you can say, okay, yes, but I didn't like the fact that say the emissions were a linear function. Could I do something about that? If they're kind of weakly nonlinear, so f here is a nonlinear function, we can maybe linearize around our current estimate Zn. We can linearize this function here and do that. That's quite an old-fashioned idea. There's some nicer, well, now going back actually almost 20 years. This is Andrew Blake, who's there. Well, I think he's still the research director of the Turing. Will be stepping down soon, and I'll show you that in a minute. And there's a whole bunch of other work. Say these methods known as particle filters are one way of doing this. So we can essentially trying to maintain this distribution. We want this P of Zn given x1 up to xn, that filtering distribution. We can try and maintain that not as a Gaussian, but maybe as a bunch of particles that sort of non-parametrically represent that. Let me see if I can find the demo here. Yep. Okay, so hopefully this will play. So this is a very old demo, one of the first ones that Andrew Blake and his student Michael Izzard did. What they were trying to do here is to track a leaf. So we can have fairly simple dynamics about maybe where this leaf is going to move over time, but the relationship between the outline of the leaf and the image is a very non-linear process. So they introduced what they call condensation, but more latterly was called particle filtering, to basically address trying to do this tracking problem. So a lot of these tracking problems, say in video, have this kind of non-linear behavior, and then we'd want to use something like a particle filter to address that. So one thing we can do is we can take the Kalman filter, and then there's a bunch of kind of elaborations of that we can use for different situations. So one is a switching Kalman filter, then a factorial switching linear dynamical system. We can talk about that in control theory. We can talk about conditional random field and neural nets. Let me just say sort of essentially one slide about each of those four topics. First of all, with switching dynamical systems, this part here, if we emit these squares at the top, this is our Kalman filter. This is our Linear-Gaussian HMM. But what we can do is we might believe that there are different regimes that the system might be in. You know, maybe a person is running or walking or so on like this. We might want to model their motion under these different situations. So one thing we can do is have a discrete variable here, which is the type of motion, and then we can have dynamics conditional on that motion. And then if we see a sequence where somebody is, say, transitioning from walking to running, we'd want to do inferences here on these switch states here and detect that, and also model them in these different regimes. So it turns out that basically for both discrete models, for HMMs, and for linear Gaussian models, we can do exact inference. At the fear of some contradiction, I think they're basically the only two situations we can do exact inference. So certainly it's proved by Lerner and Parr that we can't do exact inference in this switching linear dynamical system. However, there are a number of sort of approximations that are used in practice and can work quite well. So yeah, we might see this from, for example, for different for switching between different regimes in dancing, or also other people have used this, for example, identifying activities, maybe different gym activities that people are doing and things like that. So yeah, the switching linear dynamical system is a kind of nice extension of the LDS to take into account that we might have different regimes. One thing that I did with my student John Quinn and also a clinician Neil McIntosh is that we wanted to actually use this kind of model to model observations of initially we were in a neonatal intensive care unit, so we'd have observations of blood pressures and temperatures and so on, and there's some underlying physiological state that's evolving in time. This is for a neonatal baby. And then we might think that there's some different factors that are involved. So maybe, well, one thing that can happen is that there can be a drop in heart rate. This is called a bradycardia. So we might observe that might be happening or not. That's a discrete variable. But there might also be actually different artifactual factors. So one example is that if we take a blood sample of the baby, actually we don't observe really what's going on with the baby. We just observe an artifactual process of a pump pumping against a closed tap. So we need really to think about having this state split up rather than just one switching factor. It's useful to think about this as a bunch of different factors. Now, you can say, well, I can just take the cross product of all those, and that's one bigger switching factor. That's true, but actually the way that these interact with the variables, it's kind of useful to actually keep this separate structure, and also because we might want to interpret what's going on. So again, those things are quite useful. But again, this is a sort of extension of the linear dynamical system with the switch variables here. So if you're a control theorist, you'll say, well, okay, you told me about the linear dynamical system, but what about the control variables? If we're flying a plane, we actually want to try and get it to go where we want it to go. We can exert some influences. We can adjust what our engines do in order to actually to make that happen. So the simplest control model is to say, okay, as well as the dynamics here on the z's, we've also got some effective control variables, these u's, and so we can affect things like this. So that's one model, and then we can have an observation model that also depends on the u's. So basically, there is a whole discipline of control theory based not only on the linear situation, the linear quadratic control, which is a nice place to start, but also nonlinear variants of this. But you can also translate this into HMMs, where you can have control inputs on HMMs as well. So basically, you should sort of think that there's some freedom to sort of mix and match here. You can draw these different diagrams, think about what they might mean, and so on. One other thing we might want to do is that, so here we're assuming, I'll assume you know something about, well, here we're switching from a directed graphical model, which we've been talking to up to now, to an undirected graphical model here. And if we're particularly interested in, say, in the inference for the, say we might call these y's, given the x's, and so in this case it might be, we're very interested in inferring, trying to work out what phoneme somebody is saying at each time, given the speech signal, then we could factorize this thing like this. This is a so-called conditional random field, which is an undirected graphical model, and we're very interested in this P of y given x. Here, this is sort of, we're trying to focus on, as it were, the problem we want to solve, get these y's given x, and not modeling the joint, because in what we've been talking to up to now, we really focused on modeling that joint distribution. That's very natural from a generative model point of view, but sometimes perhaps we really want to focus on this discriminative task, getting the y's given x's. Then maybe we don't have to have a fantastic model of generating x's as long as we can generate good y's given x's, okay? So that's the conditional random field. And yeah, okay, so let me now talk about recurrent nets, and I'll certainly admit that these were borrowed from my colleague Steve Reynolds at the University of Edinburgh. So one thing we can do is to kind of think about what we've been doing and what kind of dynamics we've been using in these different graphical models, and how we could kind of relax the fact that we had a very probabilistic interpretation, and maybe what would happen if we just sort of take this sort of dynamical structure. So one thing we could do when faced with a time sequence, and so this is time t minus 2, and there are 3 x's here, time t, t minus 1 and time t. One thing we could do is use what's called a sliding window. we can kind of try to predict what's happening at time t, given a window of context of the x's around it, and slide that along to make new predictions. This has the sort of disadvantage is that we're only taking in a finite window of context, and sometimes there can be things that happen. There might be something that happens early on in the sequence, and that kind of does something like set a bit, and then basically you're waiting until in the end, much later on, you kind of you need to know that that bit was set. For example, if you want to balance parentheses, then you have to remember that you say you've started the left paren, and then you have to match it with the right one or something like that. So just using a finite window of context is not a very elegant solution. So the thing that we might want to do instead is we've got inputs, we've got some hidden state, okay, and that's like our Z. And then we've maybe got some output task, so we might, like those Ys, so we might want to predict again something like these phonemes given the input of speech data. And one of the attractions of this is that this can give rise to potentially infinite context rather than just this finite window of context from the sliding window. So one thing we can think about is what does this dynamics do if we don't have any input? We can do a number of different things. There's a whole theory of dynamical systems, and we could do things like settle to a fixed point. We can have sort of stable attractor. We can maybe create some stable oscillation. We can have chaotic dynamics, and so these are the kind of things that could happen in the recurrent net. And one thing we might want to do is to create memory of past events in this state that we're keeping hold of, maybe events that are important to future predictions. Another thing is that we can sort of think about, in the same way that in the Kalman filter, for example, when we computed P of Zn given x1 up to xn, we compressed all the information from the past into a distribution of Zn. And because of the Markovian structure, there wasn't anything else. That was all we could need. So in the same way, we might compress the whole history of a sequence into some recurrent state, the state at time t. So yeah, okay, let me first of all talk about vanilla RNNs. So if you're familiar with standard neural networks, what we're going to do, say here, if we've got some input, let me just have a look. Yep. Here we've got some input at time t. We've got, say, some vector of inputs indexed by s, and this is we have a weight matrix here which maps from those inputs to some hidden units, such as the linear transformation, and also because we've got a recurrent connection here, we've got the hidden units at time t-1 that we've kind of copied from the previous time step. And we're going to have some recurrent weights here, and that's mapping from this vector of hidden state with a weight matrix here. And so these hidden activations at time t will depend on both the x, the input, and the hidden state at time t-1. And then the standard thing we would do in a neural net is to put that through a nonlinearity, so something like a sigmoid function. So, and then we can have some other mapping here between this recurrent state at time t and the output if we want to do a task that requires that output. So if we unfold this in time, then what we've got, say at time t, is we've got this input mapping through weight matrix W1 to the hidden units at time t. We've also got these hidden units at time t-1 mapping through the recurrent weights WR to the time t here. And then we've got the output depending on this hidden set. And then we can push this process through time. We can just keep doing it. So this is the next time, t plus 1, and so on. So we can think about unrolling this network like this. And one reason that's sort of interesting is you can think of this as a deep neural net, where you started off, say, with inputs way over here at time 1, and now you're getting some output at time t plus 1 that depends on that whole sequence of inputs, including, potentially at least, those early inputs. So if you're familiar with neural nets, you know that the normal way that they're trained is through backpropagation. So if we want to get this output maybe our net at the moment hasn't been trained to predict that well. We might calculate an error between what it should be and what we're predicting. And then what we can do is back propagate those errors. And as you see through these red arrows, they back propagate all the way down this hidden chain. Now that's sort of interesting, although it does have its problems. That actually there can be dangers from having this long sequence of hidden activation. So yeah, one other thing to notice is that actually all these weight matrices here are actually constrained to be equal, right? Because they're basically the same copy at each time. So to do these derivatives, you actually just have to add up at each time. We'll maybe get a contribution here, another contribution here, and so on. So basically, the derivatives with respect to the weight matrix, which is sort of copied everywhere, just add up. The other thing we wanted to talk about is that to obtain these backpropagation through time, BPTT, we will take the product of many gradients. Basically, when we do backpropagation, we get all these products, and this can lead to a problem. Basically, perhaps most likely, to get vanishing. If you get a whole load of gradients smaller than one, they kind of shrink away, or potentially exploding when you get very large gradients. So there's some tricks that you can do. So there are things like RMS prop and other methods of trying to deal with this. But another thing you can do is also to say, well, maybe we want to be more careful about how we organize that state and how we organize the effect of the previous state on our current state. So one example of this is the so-called long short-term memory, LSTM, and introduced by Hochreiter and Schmidhuber. And here, it's probably quite hard for you to see the text from the back, but basically what they've created is something where there's some state, and then there's a so-called forget gate. So either the next state will be some multiple of the previous state, then plus some change on that, or something looking at the effect of the new stuff. And so structuring this model like this with the sort of explicit remembering rather than just kind of folding it into the standard neural net machinery actually turned out to be quite a good idea. And it makes these things easier to train because they're better conditioned. And also can sort of essentially explicitly remember stuff until the forget gate tells it basically, you should forget that now, pay attention to this new input. So that's certainly one of the workhorses of current time series neural nets. So we might do things, so for example, speech recognition going back to Tony Robinson in the 90s, they were using recurrent neural nets, rather in advance of the wave there. And basically they got killed by HMM technologies at the time, but sort of 20 years on, that kind of model was shown to be very effective. We can also use these LSTMs for speech recognition, and if you have this long short-term memory, you can stack these up in various creative ways. And so this is an example of playing with those different structures. You might also want to predict language, so you might want to consider the sequence of words that someone's speaking. And you might want to predict the next word, given, say, input, which may be the current word, but also, say, some state information we've taken into account from the rest of the sequence like that. We want to predict the next word. So again, these kind of models have been quite successful in that kind of task. And one other very nice sort of task that has been quite successful with is so-called neural MT, neural machine translation, where we might take in a sequence of words, say in Spanish. We compress that representation into some state here, and then we decode that state into, say, English over on the right-hand side. So these are a couple of papers from 2014 that were doing this, and this certainly now, I think, is the sort of dominant methodology, for example, in machine translation. So one final example of this is we might also want to, we talked about doing modeling different motion regimes, we might also want to do that maybe for modeling, say, motion capture data. So probably in making movies, you'll be aware sometimes they want to put markers on actors, and they track those markers through time, then they transfer their motion onto maybe a cartoon, an animation or something like this. If we have that kind of motion capture data, we might want to model that, and we can think about, again, having some sort of mapping from the x's, the inputs, to some recurrent state, and then that a recurrent state evolving in time under some learned dynamics, and then also emitting y's, which might just be x of t plus 1, for example, if you want to train this model. So we can sort of take the same ideas that we had in the, say, the Kalman filter, but there we were kind of restricted to linear and Gaussian observations. Here we can kind of make things more nonlinear. One thing we have lost, actually, you'll notice, is that we don't actually have real representation of uncertainty here. We just have a point in some hidden unit activation space. There is some work on trying to make that more probabilistic, but the general standard neural nets don't do that. So there's some underlying dynamics. And you might think that, for example, we talked about these different regimes of walking and running. Maybe somewhere in the different parts of the hidden unit space, there are sort of different dynamics for those things that are going on. But it's a very non-explicit and also very uninterpretable representation of the dynamics. Whereas you have to work generally quite hard to try and figure out what neural networks are actually telling you. Okay, so I think, just to summarize, we talked about Linear-Gaussian HMMs, or Kalman filtering, and then we've sort of gone beyond that, both by looking at richer graphical models, but also by kind of removing our probabilistic spectacles and thinking about the recurrent dynamics that we have in things like Kalman filters and HMMs, and making that more nonlinear and ending up at recurrent neural nets. So, happy to take questions.